Embark on a journey of inspiration and discovery with the Purdue Lecture Hall series, proudly presented by the Purdue Institute of Inflammation, Immunology, and Infectious Disease. Join us as we delve into the remarkable odysseys of these aspiring scientists, each crafting their own narrative in the world of science and groundbreaking research. Take a glimpse into their diverse cultural backgrounds and the journeys that brought them to Purdue University. Thank you for watching the Purdue Lecture Hall series. Remember to hit the like button and subscribe to our channel. Welcome, everybody. My name is Tommy Soares. I'm Director of Scientific Strategy and Relations at the Purdue Institute of Inflammation, Immunology, and Infectious Disease. And today I have the pleasure of welcoming Humberto Monsivais from Ulrike Didak's lab here in the School of Health and Human Sciences. Humberto is doing some wonderful work in his PhD, doing magnetic resonance spectroscopy, magnetic resonance imaging. Welcome, Humberto. Thank you so much for being part of the Purdue Lecture Hall series today and presenting for us today.
Yeah, thank you. Thank you for the introduction. So now just go ahead and share my screen.
Absolutely. I'm going to let you take the spotlight as usual, and you can go ahead, share your screen with us, and I will turn myself off and let you go for it.
Okay. That's good. Can you see it?
Yeah, we see the we see the PowerPoint. There you go. Perfect. Okay. Awesome. Take it away.
Okay. Thank you again for the introduction. My name is Humberto Monsivais, and I am a PhD candidate in medical physics, working with Dr. Ulrike Didak at the School of Health Sciences. And today I will just share about a lot of some of my research. The title of my talk is kind of broad, but it's like, can MRI detect hidden metals in the brain? But first, I'll give you a little bit of my introduction about who I am and where I came from. I'm just going to put this like this here. So I graduated with a bachelor's in physics from SFA. SFA is located in this little town in Texas called Nacogdoches. Originally, I'm not from the U.S. I was born and raised in Mexico, but I moved to the U.S. when I was 15 years old, and I just went to a local college after graduating high school, and that's where I just kind of learned about science. It was my first introduction to university setting, so it was a great experience. After that, I went to the University of Texas at MD Anderson Cancer Center, where I worked as a medical physicist assistant in diagnostic imaging. That is where I found out about this medical physics field in general. Being an undergrad in SFA, I didn't really know what my options were as with someone with a bachelor's in physics. But then I found out about this other field that combined physics use physics to inform the needs of medicine, try to address some of the medicine problems in from the physics point of view. So I worked there for about 4 years. And then I decided that I wanted to do more, not just be an assistant, but actually become a medical physicist. So I started the graduate program at Purdue in 2019. I came in as a master's student and started working right away with Dr. Didak. I really liked the whole unique application of medical physics that she had going on in her lab. The most common application of medical physics is typically in cancer research. But in here at Purdue, we were doing addressing environmental health or toxicology concerns using MRI. So that was really cool, and I really fell in love with the research. So I stayed for my PhD. Oh, this is a typo. I'm not in my first year. I'm actually in my third year as a PhD student, and I'm in my last year. So I will be graduating in May, and so I have made quite significant progress in my research, and that's where I jump in right now. Okay, So in our lab, we study manganese. You may not have heard about manganese before at all, but it's a very abundant element in the Earth's crust. It's the 12th most abundant. It's used in a lot of industrial processes, so like welding, mining, making batteries, grinding ore, things like that. But it's also an essential trace metal for us as humans. So we all have manganese in our bodies. We need it for to regulate the growth of our bones, and the energy metabolism, and it actually protects us against some oxidant species or free radicals that can happen in our body as a result of oxidative stress. However, the problem becomes when there's an overexposure of this metal. And that typically happens, the most common way that it happens is in the welding setting. And that causes a lot of problems. So it can cause problems similar to Parkinson's disease. Here, I'll go over here. So it is known, the first sort of like case of manganism happened in 1837 in a manganese-based bleach manufacturer. So these people were exposed to airborne manganese by making bleach, and they noticed that the symptoms, there was no protection at all. Probably they were all about like motor symptoms, like they will get stiffness and tremors, some sort of like reduced arm swinging, things like that. Rigidity and tremors in the head or the extremities. And at that point, whenever you get to this extreme symptoms of manganism, there's no coming back. There's nothing that can fix it. Even the drug that kind of helps alleviate the symptoms of Parkinson's, it doesn't work with manganism. And then at the early stages of this sort of like disorder, sometimes it's called as manganese mania, because it affects your cognitive function. So it affects your mood, your memory. You might change your personality a little bit, so you're more aggressive or irritable. And also your psychomotor skills. So for example, you might have trouble concentrating or learning new things. And that is why it's important to find ways to avoid getting to this point. So we don't want workers in the welding industry or any sort of industry that they do a lot of manufacturing with these metals, that they get to this point, because there's not much known about whether some of these symptoms are irreversible or not. And then iron is another big component of the welding fume. So welders, in our case, like, they're not just exposed to one metal. It's not like they're just welding and the fumes only contain manganese. They contain a mixture of metals. They contain aluminum, chromium, of course, iron, and some others. But iron is 10 times more present than manganese in the welding fumes. And although it's not recognized to be a neurotoxic, like a toxicant, iron homeostasis is typically associated with oxidative stress and neuronal death in many neurodegenerative diseases, such as Alzheimer's and Parkinson's. And they are actually pretty similar in their chemical structure. Manganese and iron are not that different. And it's been proposed that they can replace each other in their processes. So this little cartoon right here just showing that if there's some iron transporters, but there's no iron to transport, then manganese can take its place and continue to the downstream process. Same thing with if there's some manganese transporters. I mean, some of them share the same one, and there's no manganese, then iron can take its place and then do its processes as normal. But it's still not very clear. And then the field of manganese neurotoxicity, most of the time, it's just been concentrated on manganese and not what the other metals do. So there's some knowledge gap, basically, because all the signs of manganese toxicity are neurological, it is critical that we understand how this excess accumulation and distribution of manganese and iron affects the brain. So this is where my research comes in. Like, I try to sort of like answer this whole mediation process. So if there's metal exposure, what does the brain do to, how does the brain deal with this excess metals? And then how is that associated with any sort of health outcome that we might see? So the brain is a mediator, and then the metals exposure is sort of like the cause of these things. To do that, we had to be able to see it, to quantify it, and then find the associations between how all these things are related to each other. The way we can do that, the only way to not the only non-invasive way to detect metals in the brain is using MRI. MRI provides excellent anatomical contrast. It's been used in a lot of medical applications. If you're gonna have surgery in the brain, for example, someone's getting a glioma taken out, like they do a lot of MRI imaging to figure out where it's located, how much of their brain it takes. And you cannot do that with any other modality like CT or ultrasound, because they don't have this contrast between soft tissue. Why? Is because most of our body is made out of water. So like 60% of the body is usually hydrogen. And here's just some basics. So think of these hydrogen atoms, they're like little magnets, they're spinning in random directions in our body. But if you apply an external magnetic field, such as the one that comes from an MRI, they all tend to align in the direction of the magnet, the main magnetic moment. And they create this, like what we call a net magnetization vector. This is not very useful in this at this point. So if you think about it, you're laying on the scanner. Imagine that this is the bed, and then the magnetic field aligns in that Z direction. So right now, all the magnetization is in this direction, like I said, but that's not very useful. So we had to apply another RF pulse that can be used to spin them out of equilibrium. So basically, it knocks them like at 190-degree angle. So now the magnetization is here in this position. So it's been we apply some energy to the spins, and now they're out of equilibrium. If we stop this the application of the RF pulse, they will spin back to the equilibrium position, and that is what causes the contrast in our imaging. So whenever this external RF pulse is turned off, the MRI we have another sensor that is detecting when the spins are relaxing back to equilibrium, they're releasing energy. And there's another coil, this other detector here is a receiver coil that is detecting this signal. It's a free induction decay curve. So it's basically, think about it like it's not here, we stop the processes, and then it starts to build up again. And it is this, every tissue in our body has a different type of relaxation. So not everything relaxes at the same time, and that's what causes the contrast in MRI. So the main two, processes going on is one is called T1 relaxation, which is basically the time it takes for the spins to flip back to equilibrium. And this kind of represented here. So just think about it like if what we had here, how long it takes to build up again to the equilibrium position. That is what T1 is. At the same time, we have T2 relaxation, and that is basically the time it takes for these little guys right here. They're typically all aligned, like here they're all in phase, but then they start to dephase. And that's another contrast mechanism in MRI. So that is called the T2 relaxation time, which is called transverse relaxation or spin dephase, and that is represented by this curve. So typically, this is just you will see this in MRI like lectures and textbooks a lot. There's another relaxation time called T2 star. That is basically it's an effect of all the imperfections that we have in our equipment to measure the T2 relaxation. It basically it reduces the time it takes. It just makes it basically worse. They start to dephase at a higher rate because there's the field is inhomogeneous, or there are other things in the tissue that we're measuring that is causing this defacing to happen at a faster rate than normal, and then this is called T2 star. So how is it measured? So because MRI allows us to like target specific metal ions non-invasively, and these are metals, so manganese and iron are metals, and we have a big magnet. So not all metals are what we call MRI visible, but manganese and iron happen to be those type of metals that we can actually see with MRI. So, but we're not measuring, I had to like sort of emphasize that we're not measuring signal from these metals. We're measuring the effect that they have on the surrounding water, essentially. So if I have manganese in my white matter, that affects how the white matter relaxes. I'm not measuring signal for manganese necessarily. It's just the effect that it has. So manganese happens to be a paramagnetic metal, and when it's bound to tissue, it shortens this T1 relaxation time. So if this was the normal relaxation time, this black line, if there's manganese, it will shorten it and make it, smaller. So this is what this blue line does. With iron, it's ferromagnetic, and when it bounds to tissue, it affects the transverse relaxation time, the T2 star that I mentioned before. So just imagine same thing. This was the normal line if there was no iron, but if there's iron, then it becomes shorter. How does that look in MRI? So here are some examples. This is a T1 weighted image of a healthy control. Everything looks nice. There's nothing abnormal to pinpoint. However, in a welder, when there's manganese, the hallmark of manganese exposure will be this hyperintensities in the globus pallidus. So this area is just brighter, and that is due to this shortening of the T1 relaxation time. And when we do T2 weighted imaging, right, we're trying to see the effects of T2 star or T2. A typical control will look like this. There's nothing particularly like abnormal to see about. Like normally you do see these dark spots, but if we compare it to someone who's exposed to the metals, they'll be even darker. So just think about it like darker signal here means more iron, brighter signal here means more manganese. But these are very sort of like qualitative approaches. So there's nothing, the signal is in arbitrary units, is just some number, right? There's more signal here than there's more signal in the background. Same thing here, like there's just more signal here than here. It's not very specific to anything per se. Like there's no way I can tell you like, oh yeah, because this is brighter, so much more manganese is there. Another approach that is more quantitative is called T1 mapping. So these images are not about, the signal here actually represents a relaxation time. So it's a value in milliseconds. We're like quantitatively measuring a physical property of the brain. And because manganese is a T1 contrast agent, as manganese increases, it shortens the T1 relaxation time. So in T1 mapping, the darker it is a brain area, then that means there's more manganese. So that's just a little counterintuitive. I think the most intuitive way to present it is R1. So R1 is the inverse of T1. So R1 is 1 over T1, and that's this other image on the right. And that's more, I think, is easier to understand that, yes, if the signal here is brighter, then there's more manganese. So we typically use this R1 maps instead of the T1 maps to present increased signal with increased manganese accumulation. This is one of my papers that's currently under review. Basically, we use a whole brain approach using this R1 maps to figure out, do a group difference statistical test to figure out where in the welder group we see increased signal of manganese. So one, like I mentioned before, the globus pallidus is in the basal ganglia area, and which is this like really hot spot that you see in these images. That's where most manganese tends to go to those areas at the very beginning. So this is just showing that manganese doesn't just stay in that brain area. So it seems to diffuse along this, what we call the white matter tracts. This is what these red lines are. They represent white matter tracts, and it spreads to larger areas of the cortex, specifically to cortex that are associated with motor and cognitive functions. So here in this other lower panel here, we see that it actually goes to the cerebellum and the frontal cortex and the hippocampus. And we find that this excess accumulation of the metals is associated with some other motor metrics, such as the UPDRS, which is a scale that is used to assess Parkinson's symptoms. So that is one of my, so this is just really nice to see, because most approaches before have been very focused on only this specific brain area, the basal ganglia, and not a whole brain approach. And this allows us not just to visualize it, but also try to find some correlations between where the excess manganese is associated with other sort of metrics of exposure and metrics of health outcomes. Iron, and like I said, we also are concerned with iron. So this is hasn't been much of a focus in the field. So I'm starting to do that in our lab. And the first step that I wanted to do is compare two MRI methods that is commonly used for iron imaging. So here is a phantom study that we performed last year. So basically, we build this phantom. A phantom is just some sort of a object with non-geometry, and we know a lot of characteristics of it. And we inserted different vials that correspond to different concentrations of iron. So it goes from a really low concentration to a higher concentration. And we wanted to assess what is the linearity of the signal compared to the concentration of the metal in there. So we use R2-star, which is commonly used for iron assessment, and also quantitative susceptibility mapping, which is another technique that is that measures the susceptibility of metals or other things in the brain. They have a very specific contrast mechanism. So in R2-star goes linearly with manganese concentration. So the brighter it is, the more there is. Same thing with quantitative susceptibility mapping. Positive signal means more metal accumulation. This just shows that both of these methods are very sensitive to to iron. So the top curve is just R2-star versus iron concentration, and it's a very nice linear relationship. And the same thing with QSM. So there is just a confirmation that our sequences are working, and it's sort of like a calibration curve if you want to measure something in vivo. But how does that compare in vivo? So here I have an example of a R2-star map of a welder, and it's the quantitative susceptibility map or the QSM map. And we find that in the globus pallidus, there's a strong linear relationship between both signals. So R2-star and QSM show a very nice correlation between metal concentration and signal. But in the substantia nigra, which is another very difficult area to image, the R2-star seems to be a better approach, better technique to measure the signals there. And when we look at group differences, the statistical significant group differences is for R2-star. We see it in both the globus pallidus and also the substantia nigra, but QSM is not significant in substantia nigra. Some of the explanation to why we don't see the same significant differences. The substantia nigra, like I said, is a very hard area to image. It's very deep into the brain, so there's signal loss. It's a very small area, so there's a lot of more of what were called inhomogeneities in that specific region. But in the global spotlight, it's a very nice uniform area, so it's a little bit easier to measure the signal here than it is in substantial Niagara. But it's still pretty preliminary. You know, we're still looking into how we can better compare these two methods and make more interpretations based on those results. This is another project that is more of on the exploratory side, working with a novel 3D ultra short echo time sequence that uses a Rosette K-space pattern trajectory. We actually published this in one of the journals where instead of using R2 star or R2 as a proxy for iron, we're using a T1 weighted signal. So this is based on the same phantom that I showed before, but with a different sequence. Ultra short echo time means that so typical echo times in MRI are in the millisecond scale, like 2 milliseconds, 5 milliseconds, 30 milliseconds. Ultra short echo time means in the usually it's like 100 times shorter, so like microsecond scale, or so like 20 microseconds, 1 microsecond. I don't think anyone can get to 1 microsecond, but 20, 50, 100 microseconds is what we would consider ultra short echo time. The advantage of this is that basically we can sample the decay of T2 at shorter time intervals. So anything, like I said, manganese typically iron has a short T2, and if there's more, it's even shorter. So that means that we need to sample its signal before it decays. So that's the advantage of using an ultra short echo time sequence. In this particular setup with the flip angle combination, the short TR, it sort of is in the T1 weighted domain. And we see here in this curve that at the different echo times, we see this relationship essentially. So this was a very sort of like proof of concept type of project where it was done on healthy volunteers. So the top row here shows what the UTE images looked like before we applied this sort of like correction. We like basically saying, okay, take the signal, fit it to this line, and then give me back what you can see. And we saw that all of the iron-rich areas are highlighted very nicely after we applied this basically we modulated the signal with this relationship. So I'm trying to do the same thing. So this was in healthy volunteers. I'm trying to do the same thing with in our cohort that we have controls and welders. You see something very similar. This is still very preliminary, where like this is a match age control, where there's no excess, there shouldn't be any excess metal. And then on the welder side, we see that these areas here, like the globus pallidus, some parts of the thalamus, the basal ganglia are very nicely highlighted, indicating that there's excess metals in there. So this should be, or the exciting thing about this could be a more accurate way to quantify the excess metals, in particular iron. And yeah, so like this is still a work in progress, so not much, just very excited about this preliminary results at this point. Nope, not going. Okay, now this other approach is still on manganese. Is very novel in the sense that I'm combining our quantitative MRI measures with network science. So what is network science? It's a field study that looks at how different brain regions communicate or interact with each other. Network science is usually applied in looking at function connectivity. So if you have a task-based fMRI or resting state fMRI data, you can build this sort of like networks where you try to see how the different connections throughout the brain are related to each other. We don't have that type of data. Instead, we have relaxation maps. So the approach here will be like to see how the changes in these relaxation properties are associated with manganese accumulation. So instead of me using bold signal or bold signal that is typically used in fMRI, I'm using R1 signal to try to construct a network that tells me how is the manganese in the cerebellum associated with the manganese in the basal ganglia or something like that. We call this relaxometry covariance matrix to try to see how the brain's mediation mechanism to metal exposure. So I'm just showing like a breakdown of the data that we have. So for this particular project, I'm using data, what we call the WABA study. It uses 26 controls, 36 welders. They're all nicely aged. Their age is matched. Controls have no years of welding. Welders about 12 years. And there's some metrics of exposure, like their airborne exposure. Controls really don't have anything, and then welders. So basically, we take their anatomical images, what's called an MP-RAGE. It goes through this pipeline called FreeSurfer, which basically cuts the brain in like 192 brain regions. And half of it comes from like the left hemisphere and the right hemisphere. So it basically gives me a volume of, let's say, the globus pallidus from the left and the right. It gives me a volume of the putamen, the caudate nucleus, the thalamus. All that basically gets cut up and like outlined into a file. It uses the specific atlas here. Then when I just average the two hemispheres, or basically I overlay this what I call the segmentations, right? So this is just showing like, okay, yeah, this area belongs to the thalamus. This is the caudate nucleus here, the putamen, the globus pallidus. I overlay that onto my R1 maps to extract the R1 values from that brain region. And like I mentioned before, my R1 value is proxy of manganese accumulation. Then you build this matrix where basically an entry in one of these matrices represents the correlation of metal accumulation between one brain region and across another brain region. And this is all at the group level. So just think about it. I have the mean globus pallidus signal from the welders. And how does that correlate to the mean signal of the putamen or the white matter or the cerebellum? And that's what these matrices are. So all the brain regions here versus all the brain regions. That's why you see this nice linear relationship in the middle, because it's just one brain region correlated with each other. So this is for the healthy control group, and this is for the manganese exposed group. Just looking at it, you sort of see some differences. So the more yellow or brighter yellow you see, that means there's a high correlation. In the healthy control group, yes, we see a similar pattern on here, but we just see a lot more yellow throughout. So that just tells us there are more brain regions in the manganese group or the welder group that are coupled with each other based on this R1 measurement. The most interesting part is this subtraction matrix here. So if I take this matrix, this matrix and subtract this other matrix, wherever I see more yellow, that means that this group had a lot more correlation versus the control group. So just showing here that in the color scale, yellow means manganese was more present in the welder group and in the healthy control, and blue just means that there was less. We don't see a lot of blue, right? So like it's just because that we have the R1 is sort of like the same in both groups, but there are very specific regions where that's not the case. So that's what this yellow indicates. To sort of assess the covariance or like how these things are changing in relation to each other, I take the sum of every column to give me sort of a metric of covariance. And that's what this is here. So A high covariance change indicates that the accumulation of the metals in one brain region is spreading more to other brain regions in the Wilder group than in the control group. So, and low values indicate that there's a similar tendency to accumulate, but in negative values, there's no accumulation. So what this is saying is that if I add up all these rows here, if this value is high, that means that that specific brain region, like brain region number 20 or 10, is sort of coupled with other brain regions. It's like spreading the manganese. But if it's negative or low, that just means that that brain region is not spreading the manganese to other brain regions. It's just keeping it in, and it's something that we will call a silo, and you'll see what I mean by that. So this is just a little snapshot. Like if I take, for example, the thalamus has a high covariance change, so does the putamen, the globus pallidus, the brainstem, and things here, they don't, these are low values. So this is basically allowed me to identify brain regions that are silos and propagators. So a silo will be a brain region that has a significant metal accumulation in the welders with respect to the controls. So that means like if I were to do a t-test of the R1 mean between the globus pallidus in the welder group versus the control group, the welder group will have a statistically significant higher value. So that's important because like we had to make sure that there is some excess manganese. I cannot just say, like, oh yeah, my covariance value was high. Like that just means there's more. So we had this condition where like no, like this specific brain region does have higher signal than the control group. And actually, you have to have a low covariance change. So that means there's no that brain region is not coupled with anything else. It's just keeping all the manganese in. A propagator also has a significant amount of manganese, but has a high covariance change. So that's what we will call a propagator. And here I'm just showing like a little overview. If I put all of my 92 brain regions in this plot, and I plot the covariance change versus the x-axis is the T1 the T values to show where the cutoff is for significance. So it's right here in this case in this red line, and the y-axis is the covariance change. So if I define a value like a threshold of okay, below this value, I would not consider that low covariance change, and above this value is high covariance change. This is just to make it symmetric. It's center about 0 here. And so the lower quadrant here, that means if you're like on this far side, you're on the significant side, and you're in the low covariance change. So these are whatever falls into this area will be considered a silo. If something that falls on this upper quadrant here is also on the significant side, but has a high covariance change, so that they don't only accumulate, but they're also propagating to other brain regions. This side is not so much interesting. There's no accumulation, no propagation. Fine, like this, it's okay. And then this one has also no accumulation, but somehow there's sort of like a like the middleman in the propagation of manganese. So the brain regions that fall in this area, they're not necessarily accumulating manganese, but they're involved in some of this propagation process. Or yes, that's what I'm saying. So like I said, I just explained it here. If I summarize it on this table here, so what we found as a silo is the globus pallidus. It seems to align with what we already see in the literature. The globus pallidus is the hallmark of manganese accumulation. It's the first area that shines in a T1 weighted image, and it's associated with this function. So it's movement control, inhibition of unwanted movements. So it makes sense. Manganese affects motor function. It's a nice sort of a confirmation for us that this method seems to be working. Another areas that were sort of like accumulation. So the putamen is also in the basal ganglia. The nucleus accumbens is also in the basal ganglia. All these things are, you see, motor control and learning, reward system motivation. And then these areas with the asterisks, they didn't have any significant manganese accumulation, but they had really high covariance change. So the corpus callosum is the area that connects the two brain hemispheres, and they're full of white matter tracks. And it's I sort of emphasize that white matter is what we saw in my other study, where we see that manganese seems to diffuse along the white matter tracks because it acts as a calcium analog. So it gets taken up by synapses and it just diffuses along these areas. The hippocampus also, I showed that in the early slides too, like that was associated with some manganese exposure. Here it's also showing like there is somehow involved in this distribution of manganese. The cardiac nucleus is also in the basal ganglia. And then just cerebral white matter is a very broad term. So basically this is all the white matter in the brain. So this is what we call the communication pathways. So all that like sort of like this just makes sense that all these brain regions that we've sort of isolated have functions that are related to memory, to like the spatial navigation, cognition, emotions, control, motor control. It's just a nice confirmation that our method is working. The propagators, like I said, there's the thalamus. The thalamus is the relay station for sensory information. So it's sort of like it just projects to very many different areas of the brain. The amygdala also is this like fight or flight response, and then the optical chiasm for visual information. So yeah, like, but how is that helpful, right? Like, okay, I identify these brain regions. What does it mean, like, in terms of health outcomes? So, okay, this approach that I just described, it sort of like lets me isolate which brain regions I need to concentrate on. Like, instead of me trying to blindly go through or just concentrate on one area that I know for sure that there's manganese, how do I know what else should I concentrate on? That's what this helps us do. Then we can try to concentrate in these brain regions to see if there's any correlation or any association between the excess metals in these brain regions to other exposures, metrics that we have. So we have motor metrics, we have their exposure metrics, cognition metrics. How does that, are these brain regions more susceptible to symptoms and things like that? So that is what the goal of this, the sub aim of this approach is to determine if there's any association between these key brain regions and motor and cognitive deficits. How do we do that? We do that with a very specific sort of like statistical test called canonical correlation analysis, which allows us to basically find the relationship between two sets of variables. And these two sets of variables can be anything. So our one set of variables will be the R1 values that we have from our brain regions. And then the other set of variables will be our neuropsychological battery tests. And it tries to figure out a linear combination that essentially tells you like which characteristic is, or what variables from this domain one is better describes the relationship with this other domain, and it gives you this sort of like canonical correlation. And what it is trying to do is that it tells me the combination of these variables best describes the variables on this other side. And it's just think about it like a linear regression, but a lot of variables from one side and a lot of other variables from the other side, and then it gives you weights. So like I can explain it here. So for example, here, these are the coefficients for I have this several manganese what I would call it manganese accumulation in brain regions. How is this associated with the health or the other metrics that we have? So something here, like for example, the butamen has a high weight, and then something else here has another positive value. That tells me that possibly the butamen, the manganese in the butamen, is associated with this FFT, which is the finger tapping test. So increase in manganese in this area is associated with an increase in time of finger tapping hits. Same thing here, like increased manganese in the cerebral white matter is associated with how long it takes to complete this group pegboard test. And same thing here, like the other way around, like if something is negative, so that means if the R1 value here decreases, so does it decrease in this other neuropsychological measure. This is still also very preliminary. Actually, just now sort of like learning to work with this type of approach. But this is nice to see that, for example, the group pegboard is a test that you have to, it measures your motor execution. So it's a matrix of 24 holes or something like that, and you have pegboards and they have a group size. So you have to basically insert them in the right way to put them into the hole. So the longer it takes, that tends to indicate a sort of like disruption in your motor execution. So if there's increased manganese in the cerebral white matter, and we see that it takes longer to complete this task, that tells us that, okay, maybe it is the manganese accumulation that is causing this problem. Here with the finger tapping test, it just measures how many taps you can do in a certain amount of time. So if it's lower, that means your motor efficiency is reduced, and if it's higher, that just means that you have more motor function. The fact that it's positive is a little bit like, counterintuitive, but in general, in the literature has been shown that they're welders, they're they're very high skill at what they do. So in general, they do already have a higher sort of like control of their movements. So they will perform higher than someone who doesn't do welding, because you need that high skill. So it sort of like masks the effect of manganese. It's called like the positive work rate effect. And because we're comparing it with people that don't do any sort of welding, they're not necessarily have higher motor skills, that we tend to see this, that they have more manganese. Okay, and that is all. So this is some conclusion. Just showing that we have a novel approach that combines quantitative MRI and network science to study manganese-induced neurotoxicity. We use this CCA approach to sort of find the associations, and some of the future work will focus on using the same methodology once we have it optimized and fine-tuned to use it for R2-star iron, which is the other big metal that we're very interested in. And some acknowledgements. Here's a photo of our lab. Dr. Dalek is my advisory committee, and these are my lab members and some of our funding sources. And thank you.
Wonderful, wonderful, Humberto. Thank you so much for sharing some of your story and your research. It's just awesome to see so much progress in this field, and you really being at the forefront of it. Tell us a little bit. I mean, do you need to be fairly multidisciplinary? You need to do a lot of computation and a lot of statistics. What are some of the courses that, if people wanted to get into this field, what should they be taking? What are some of the courses that they should be doing?
Yeah, so it is very highly interdisciplinary. So that's kind of what I love about the whole medical physics field. That is we work with so many things. So yeah, for this specific, you do need to have some sort of medical imaging experience. And not only that, but like I had to take classes in toxicology because I didn't know, what is toxicology? I didn't even know that was a thing before I came in. So yeah, taking toxicology and in general, anyone should take a statistics course because it's just everywhere. Computational size, yes, there's a lot of processing that goes on behind the scenes. Like, you can get an MRI image, but to get more meaningful information, there's more to it. I'm kind of self-taught in that way. Like I didn't take, because my degree was in physics. We weren't heavy in like computer science or anything like that. It was more math and physics. That I will seek out on your own, but if you can, just take any sort of like introduction to machine learning or any sort of like MATLAB, Python. Right now, I'm actually at a workshop in Seattle where like called Neuro Academy, where they're trying to teach us all these things, like how do you work with neuroimaging data that is not just MRI or something like that. No, and on using all these open sources, there are so many open banks like public, the Human Connectome Project, things like that. That is data available to the public to work on these things, learn these methods. And yes, it's just very
awesome,
very interdisciplinary. Yeah.
So cool, so cool. And that there are so many tools available publicly that you can use. Not only is the data there, but there are certain open source resources as well, right? Software that you can use. This is it's such a up and coming field. And thank you. I want to thank you so much for opening it up to us and having allowing us to take a peek at it. Was it scary starting in this area? Was it scary starting grad school?
Yeah, I mean, for me in general, everything was scary. Like I said, like I didn't grow up in the US. I came in, I didn't speak English in high school. So, but I made it through. I was like, okay, like, I gotta work hard and basically make my parents' sacrifice worth something, right? So it just, that's something I've been instilled in me from my parents. Like, you work hard and then you try to do the best that you can. So I just kind of live by that motto. Like, yes, like it's scary, but I have to take the chance. Otherwise, I will never know. But yeah, it was really scary. Even just thinking about grad school, like am I really good enough to get a PhD? Or like, I see all these things that are super scary, but you just have to do it. And like, unless you don't do it, you cannot live in fear of like, not take risk. Right. So yeah, I mean, now I can see that. I mean, you don't necessarily have like people sometimes, oh, like, I'm just not smart enough or something. Like that's not true. Like there's so much about your own drive to learn things. And if you're a hard worker and like you push yourself, like your mind to it, you will learn so many things. Like I'm just amazed to myself, like how much I've learned in the last 5 years, just by being there, being in the environment, talking to people, seeking out help. It's just, that's all it takes. You have to take the step to do it.
And the courage. I thank you so much for saying those wonderful, wonderful words. They're like diamonds. They're like gems, Humberto. Humberto Monsivais, thank you so much for taking time to really again let us explore a little bit your life and some of the work that you're doing, which is phenomenal and so exciting. I am so glad that you got us going in so many aspects of it that are just phenomenal, just great. Thank you so much, Humberto. I hope you have a great rest of your day.
No, thank you so much for having me, and I really enjoyed it.
Absolutely, and we enjoyed it as well. Hopefully everybody can stay tuned and hit the like button for this video and subscribe to the channel. All the best, Humberto. See you soon.
Yeah, see you. Thanks.
Bye-bye. Thank you for watching the Purdue Lecture Hall series. Remember to hit the like button and subscribe to our channel.